Okay, please come on in, have a seat. And as you're doing that, I think everybody's mic'd up and ready to go. Are we excited?
Yes.
Are we excited? Yeah. This room's a lot more interactive than the other one. I'm going to stay in here. All right, so today I have Andreas and Andrew, and they are going to be doing signed, sealed, and delivered. I don't know what it is about these titles, but I absolutely love them. You all should direct movies. Without further ado, I will turn it over to them.
Thank you so much. Everybody got your food coma going on? I'm Andrew Brandt. I'm the principal researcher at Sophos in the XOps team. And you are?
I thought you were about to introduce me too, but fine. So my name is Andreas Klopsch. I'm a senior threat researcher in the LDAPS team at Microsoft and at Sophos. And yeah, Andrew, if you want to start.
Sure. So just a quick introduction to sort of who we are. So I do malware research and network forensics, and I write about it for our blog, Sophos XOps. And in addition to all of those things, I volunteer at a retro computing museum in Boulder, Colorado, where I live, called the Media Archaeology Lab, where I study how to fix old computers and keep them running so people can come in and learn about the history of computers. In addition to all of those things, I am also running for office as for the school board in my local community. So you can scan my shirt at any time during this show and send me a campaign donation. So thanks very much. No selling. I'm not selling anything except freedom and democracy. I want to talk a little bit about a project that Sophos worked on this year with Microsoft. It actually started about a year ago, last fall, in which we discovered that some drivers that were being used in ransomware attacks were signed with Microsoft, with valid Microsoft signing certificates, and that these drivers, because they were signed in this way, they were allowed to run unimpeded on machines, and they were used to do some harm. And we noticed this in the course of doing some work with our managed detection and response team. They were getting calls in from customers saying, hey, we noticed protection is kind of failing. What's going on? So we got an agenda here of things we're going to talk about, which is about like how we discovered these things, what the drivers were capable of doing, how you can find some of these drivers for yourself, and a little bit about what we did to help end this. So let's talk a little bit about the drivers themselves. So we all know what drivers are, right? Drivers are these little software components that are used to they're used to interface with hardware devices. They're used to extend the capacity and the capabilities of an operating system. They are really important in endpoint security and detection of bad stuff. Sophos uses drivers to protect its own components from being interfered with by attackers in the middle of an attack. Otherwise, if we weren't doing that, anybody could just go into Process Explorer and do kill process, and that would be the end of your protection. But no, we use some tools to keep people from being able to do that. And of course, kernel level drivers are they have the sort of lowest level of functionality in terms of like they can get underneath a lot of other things and change the way that the operating system interacts with software at a very low level. And code signing is a really important thing because, as we know, because drivers are these like very integral parts of the operating system and they have so much capacity, Microsoft correctly surmised that this is something that they need to protect. So they invented this code signing thing that basically drivers that run at this level cannot be allowed to run by the operating system unless they've been signed with a legitimate code signing certificate. And Microsoft is one of those organizations that can sign code to allow this to happen. It's super important because signed code is a promise. It's a promise that someone has looked at the code, that it is known to be benign, that it does what it says it's going to do, that it hasn't been changed by anybody between the time that ostensibly the software developer has provided it to the company that does the signing, and it should be really difficult to get around these problems, excepting some cases where, like in the case of NVIDIA, last year there was a case where someone had, several years ago, had leaked some data from NVIDIA. It had gotten out into the public sphere, and among the data that got leaked was the private key for a code signing certificate. And what that allowed someone to do was then take any other piece of code and sign it, and it would say that it had come from NVIDIA, and the certificate was still valid, and that it would, run just like this. In that case, what happened was we discovered, or someone discovered, that that was happening, and that certificate got invalidated, and it rendered that driver no longer functional. And not only that, but no one could sign anything with that certificate anymore and continue to have it working. So I think this is where you take over. So I'll let you control.
Thank you. So as an attacker, you have, like Andrew already explained, code signing certificates, very good. As an attacker, you have two ways of actually getting code into the kernel mode or running code in kernel. The first one is you get such a certificate. The other one is you use already legitimate drivers. So starting 2022 or in 2022, we saw a huge increase of ransomware groups actually using these legitimate drivers to disable EDR agent, especially before you're doing the encryption and taking some files for ransom. And some case were Robinhood and Blackbyte or the Cuba ransomware. And one particular example of two we are going to present of such legitimate driver abuse is the abuse of the Gigabyte driver. So basically, what we've seen in 2020 is there was a ransomware attack by the Robinhood ransomware, and 5 files were dropped. So you had 2 PE files, 2 exe files, the steal.exe that executed the second one, the robinr.exe, which is a driver installer. 2 drivers were dropped. The first one, that G drive, this is the vulnerable driver that has an actual arbitrary read and write vulnerability. The second one, which is an unsigned driver, so it should technically be blocked. And a text file, which is that plist.txt file, which contains a list of different file names, process names it targets to disable. So in this attack, basically, the gdrive.sys disables driver signature enforcement, which should actually prevent such a file that is not signed from being loaded into kernel. And then the second malicious driver is run, which then targets these processes that are passed in that plist.txt and kills them. The second one, which is kind of similar, but they have a different approach, is Blackbyte ransomware. So Blackbyte ransomware is written in Go.
There you go.
And what they do, instead of trying to get like an unsigned kernel module into the kernel, or some unsigned driver into the kernel, what they do is they first identify the NTOS kernel version. And if you know a little bit about object notify routines on Windows, you can, for example, there is an API function called PSP create notify routine, which you can use as a kernel driver, and you can get notifications if a process is created or a load image happens, or for example, if a thread is started. And what they want to do is they want to disable those notify routines. So as a driver, that's an EDR driver, like some endpoint detection system driver, will have those these notify routines. And they remove it by first identifying that NTOS kernel version and getting the location of that array where all those callback functions will be entered in. So if the text is a little bit too small, I apologize. Basically, depending on the kernel version, the offset of that array will be at a different place. And depending on the version, they get that offset. These offsets are always hard-coded into the binary, and the address to that array is calculated. So basically, at that API function at the start, you will have some assembly, and at some point it will try to get the reference to that array where that is in memory. And from there, that rtcore64.sys, which is that vulnerable driver, will already be loaded. And through that first arbitrary read vulnerability, they will read those entries from that array and try to determine to which driver that callback function belongs. So you can do that, for example, you enumerate the drivers, you see the base address, you calculate the size of the driver, and if it points to the text section, you can say, okay, well, it probably belongs to this driver. And if that driver is blacklisted, they use that second, that arbitrary write vulnerability and overrides that. And those signals, those notify routines will not work anymore. So those are the two ways of, two examples of how drivers can be used, or legitimate drivers. There are many more. So VirtualBox, for example, which was very often used by the Turla group. There are some anti-cheat drivers, like from the game Genshin Impact, mHyper2. Very many anti-rootkit drivers are often used in these cases. So in the next slide, what you can see is from the behavioral protection side, the most abused legitimate drivers from the 1st of November till the 1st of September 2023. On the y-axis, you see the relative frequency. On the x-axis, you see the different driver names. But this is like just the top 10, but what you can see here is you have many anti-rootkit drivers, so anti-rootkit removal drivers, like ASVRpod, which belongs to Avast. Gmer64 is also like such an anti-rootkit driver. AMSDK.sys, which belongs to Zimana anti-malware, which was big in a report by CrowdStrike and analyzed by them. PC Hunter is also a very similar one. Then you have many drivers that use that arbitrary read and write, similar to the examples before, like in this case we have like Gdrive here, INI.io, SuperBMC, mHyper2 is also the same category. So you kind of see a little bit of a pattern that, at least in this case, many open from the drivers being abused are either anti-rootkits and also arbitrary read and write vulnerabilities. That Process Explorer one here is a little bit of an odd one out. So the Process Explorer driver from that Process Explorer tool from sysinternals, prior to 1632, they were able to kill process-protected light processes. There are some open source tools that implement some proof of concepts of how to disable EDR agents. There are many EDR killers around that tool. So in my talk tomorrow, I'll cover that more deeply, where I'm talking about EDR killers. So if you're interested in that, tomorrow I'll cover this more deeply. So right, this is like the first way of how you can use drivers. The second one is you use code signing certificates by trying to basically get one somehow. So as an attacker, you have different ways. You can say you get one from the darknet, for example, you obtain one. You breach a company and leak the code signing certificate. You might try to get your own certificate through tricking root authorities, maybe. And depending on that, you can either just sign your driver or your file, or you use a technique called signature timestamp forging. So signature timestamp forging. There is a Windows policy that before the 29th of July 2015, if the driver was created before that date, Windows will still load them. And if you do a series of hooks, you can trick around, and if you have a leaked one that has a timestamp prior to that, you can still sign your driver or malicious file. But for this talk, what's important is that Microsoft Portals one. So starting that Windows version, Windows 10, 16.07, I think, you can actually not just use like a certificate from, let's say, NVIDIA and just load it. You have to submit it through the Windows Hardware Developer Portal. And there your driver will be signed. And to do that, you actually have to have a couple of pre-requirements. One of those is you need to be part of that Microsoft Hardware Developer Program. Second one, you must obtain an EV or OV, like an EV certificate. So the difference between extended validation and organization validated is just that they offer stronger encryption and greater identity verification. So once you have those, the next step is you need to create a cap file, which includes that driver, the driver in file, the catalog files, and also the symbol file. Then you need to sign that cap with that EV certificate and submit it to that dashboard where you already have access to if you're part of that program. From there, once it's submitted, they will run a series of tests that ensure compatibility. We'll also check for any malicious intents. And if that passes, what happens is you will have a driver that has that Microsoft Windows hardware compatibility certificate. So basically, the barrier for attackers to get such a signed driver, maliciously signed driver, has increased since that version. But there are still ways. So one of the ways how an attacker could get this is, for example, if they somehow get first or leak that EV certificate, and also if they get access to that hardware developer dashboard. So if they have both of them, the third step would be that they actually submit something that passes those tests. And if you're an attacker and if you manage all three of them, you would probably get a driver that is signed by this, with that, or carries this digital signature. And we believe this is what happened in one ransomware case where we saw one of those drivers. And I'll pass over to Andrew here. He will continue and step you through that incident.
So just a show of hands, how many people use Process Explorer, the sysinternals tool? Awesome. So me too. It's the first thing that I install on any brand new machine, and it was very devastating to me to see that there was a threat actor that was using the driver for my tool. I have very strong feelings about it. I wish Mark was here. I would tell him so. Let's talk a little bit about this attack that we found last fall. So we had a team called Rapid Response that was called in after the fact to a ransomware attack that had targeted a company, and we were looking at some of the stuff that they left behind after they'd done their damage and left, but there were some files that were left behind, and we found this loader that installed this validly signed but completely unique driver that no one had ever seen before. And when we started looking at it, well, actually, I would say when Andreas started pulling it apart, and started to document all of the functionality that this driver was capable of, we started to see a big correlation between this driver and a driver that had been found by Palo Alto Networks and called Burnt Cigar by Mandiant. And we published a blog post about this because we saw that this was happening and it was bad. We then found out from some folks at Mandiant that, oh, well, maybe it's not Burnt Cigar, maybe it's Poor Try. And I would just say right now that probably what we need to do is settle on a naming convention that doesn't sound ridiculous. So here's what it did, right? So it was two pieces. There was this loader, an executable, and the killer, which was the driver. And it had this text file with a huge number of names of endpoint security tools that it would target. And that it basically what the attacker did was they would move it into the temp folder. It always had this sort of random file name, and they would start it as a service. They would start the service, and as soon as the service starts, it finds that text file that they had planted on the machine, and if there's any process with a name that matches the name that's in the text file, it's gone. And that's it. It would just run. And if those processes tried to start themselves back up again, every quarter of a second it would scan and it would look for to see if those things had come back, and it would kill them again. So here's a list of, it's a small list because we couldn't show you all 186 names and have it still be legible. So we just listed out the ones that were just targeting processes that are particular to Sophos. There were 29 of them in the list. And it could really technically be used to kill any process at all. So it was literally just a text file full of names, and you could customize it however you want, and whatever name was in that file, it would kill. There was a couple of weird things that we noticed about this driver. So we saw that it had this symbolic link that it used called KAPC helper link 1, and it was using that to kind of do a lot of its stuff internally. We saw that in strings in the file as well. And in memory, and it was using this weird IOCTL code to pass the process name to the driver and use that to kill it. And then when we were doing more sort of looking to see if we could find more examples of this, we found a few more drivers that were sort of around the same time frame, summer to fall last year. And they were all signed with these Chinese company certificates. So, when we started looking at these weird certificate drivers, we found a whole bunch of them, right? And they were from companies called like Beijing Joint Hope Image Technology Limited and Zhuhai Liancheng Technology Company Limited. They were always these kind of long names of companies that, I mean, they all sounded legit. But we could not find any evidence of any of these companies ever having existed. And in fact, there was one that was just, the company name was in Chinese, and it actually says Beijing Dongfeng Haida Network Technology Company Limited. So all of these certificates that we saw, we found 41 samples of them on VirusTotal at the time. As you know, unless you have the special VirusTotal account, you can only look back 90 days. But so this within the window in which these attacks were happening, we looked back 90 days, and we found 41 files that had been signed with these same certificates, and 38 of them had been signed with a certificate of a company that we had already classified as anything that's signed with this certificate is a potentially unwanted app. So there's this sort of gray area in the AV world of like there's known malware and viruses and worms, and then there's stuff people probably don't like, but we can't call it malware because they have lawyers. So those end up in the PUA bucket. And the rest end up in the various malware detection buckets. And as you notice, there's some real legit stuff in these certificates, like the use of an anonymous QQ address is the contact name for the certificate. So real solid fact checking here. So we started looking at this KEPC helper. The symbolic link that was in there, we noticed that it seemed very similar to something that was called APC helper that was in some of the Mandiant and Palo Alto networks research that had been done previously. And those references to stuff that were in there, some of the addresses and other things were also in that burnt cigar research that we referenced previously. So we have an endpoint security product. It's part of our thing, and we write signatures to detect bad stuff, and these are bad files. So when we got this, not only did we sort of try to figure out how it was using these techniques to kill our product, but we also wanted to write signatures that would detect them. And we do a lot of telemetry hunting to find things off of those signatures before we publish them. So we created these signatures that just went out in the world, but they were just listening and not actually blocking anything for a little while. And we found a bunch more. And we figured that some of them were also this poor try or burnt cigar toolkit. But then others seemed to be part of other sort of different families of malware. They had completely different functionality. And we started collecting them in this little spreadsheet where we were just tracking new ones as we found them in this retro hunt. Then all of a sudden, bad things happened. So some of the variants that we found were signed with the Microsoft certificate. And as you can see from the screenshot, it says the digital signature is okay. So they're okay, right? Like that's all good. We did find that KAPC helper link reference in the code. We also found that in the cases of the ones that were signed by Microsoft, they were drivers, but they had been packed with a runtime packer called VM Protect. And this is something that in the malware world we see all the time. I mean, there are vast economies, within the malware ecosystem. There are businesses that just make packers for criminals to use to hide their code. VM Protect is not one of them. They're a legitimate company, and they sell a runtime packer specifically for legitimate businesses to protect their intellectual property so people can't reverse engineer their code. But you don't see drivers that are packed, and there's a good reason why, which is that you cannot inspect the content of the driver fully unless you can remove that packer code from it and unpack the driver. So you don't see signed drivers. And yeah, so we were seeing that some of these things had the same validity, sort of timestamp ranges that we were seeing, and other characteristics that sort of matched up with what we saw in this burnt cigar thing. And in fact, like the one that was the Zhuhai Lian Cheng Technology Company Limited one had, you know, it looked like some of the same like code segments or like, you know, subroutines had just been, you know, moved into this driver from another one. So we were looking at a variant, not just a you know, completely new thing. Couple of the other similarities that we saw. So we mentioned that, like, you know, in the Palo Alto networks, they were calling them APC helper.sys. We saw this one called KAPC helper.sys. Big difference. I mean, I know, like, you and I look at that and we're like, wow, those are really different names. And then we also saw that they were in the Palo Alto network, that they were both linked to Cuba, and that the Cuba ransomware was the same ransomware that we saw in this instance. So we were looking at the same threat actor using a very similar tool to target our stuff as it had targeted another company's in the previous, you know, earlier. And then finally, like, the other thing that we saw was that, boy, these timestamps were all very similar. They were all in fact, they were precisely the same timestamp. Like, they had all been signed at exactly the same moment. So yeah, so we started looking into the details. We were seeing these validity dates. We were seeing that they were using the same valid usage data in those fields, the same validity time frame, and they were all issued by the Microsoft Windows third-party component CA 2014 certificate provider. So this is the point at which we start to take off the malware research hat, put on the responsible disclosure hat. Sophos is a MAP partner with Microsoft, and we are grateful that we've been a MAP partner for a really long time, and we want to do right by everyone. So we report this up the chain to our MAP coordinator here at Microsoft, Al Brown. Al Brown goes in, talks to people internally. We get a very rapid response from him saying, we're investigating this, we'll let you know really soon. We dig around, we find more stuff that we can give them to help them find these things. And it was in miraculous speed, 2 months from the time that we reported it to them till the patch Tuesday, where the update came out that invalidated all these signed drivers. So I was really grateful for that. It was good work, good teamwork on everybody's part. Then we publish that AV signature. And guess what happens? We start digging ourselves into a hole, and we cannot dig up, stupid, because it is really bad. So immediately we start getting reports, also from Microsoft, that we are false positiving on a whole bunch of drivers that are part of their you know, collection of files. And they periodically scan the their entire library of drivers that they've signed with every AV company whose product is in MAP. And except the problem was these weren't false positives. These were also bad drivers that had been signed in the same way, that had some of the same functionality. As we were getting these kickback reports, and we were getting them 10 at a time, and we'd get 10, and then 10 more, and 10 more, and 10 more. And for 2 weeks, we got batches of false positive reports. We then realized we had jumped into a hole that we could not get out of. So we then had to go back to MAP, go back to MSRC, let them know that those 6 drivers that we found previously, that was not the end of the story. So we provide MAP with the full data set. By the way, fun fact, you can use Yara to do all sorts of data collection and extracting of metadata from files. So I wrote this cool little Yara rule off of and ran it against the 300-400 files that we had gotten back, and used that to extract things like the P signer, certificate issuer, and the thumbprint, so that we could identify these files and give us some kind of, you know, hints as to what we would need to hunt for to find even more of them. After the work that went on internally at Microsoft, the company decided to issue a second advisory and basically invalidate the certificates for these drivers in the July Patch Tuesday that happened this year. In addition, we found out during the course of this that there is a file in Windows called drivers.stl, which we did not know existed, and apparently Microsoft did not have much documentation on either. But it is a way for the company to invalidate drivers that are doing bad things on a broad scale across the entire panoply of Windows machines. So we found out that this existed. We found out that they updated it, and thank you so much to Microsoft. You've now documented how this drivers.stl file works. And we also have a map for how to do this in the future if we see threat actors doing the same thing. The one piece that I would love to know is what happened inside of these walls when this was going on, because we sent it in, and then 6 months later we found out that the patch was being released, and we had to rush out a blog post. So thank you all. This was amazing. Great teamwork from the people in MSRC, in MAP, from our guys, from the people in the field, from our customers who were willing to look at this not as like, oh, what are you going to do to fix this problem you created, but more like they wanted to collaborate with protecting everyone. So this was just a great, good feel-good story for everyone. So I couldn't be prouder of the work that happened with us.
Thank you. So, like Andrew said, with the first incident, that was sadly not the end. So we had a little bit more of research going on, mostly that from that one driver we searched for more. We figured out that there are probably more drivers carrying that signature that it should not carry. And so we started threat hunting and doing some research in our internal databases, lots with VirusTotal signatures, to search for more of those variants or more of those falsely signed drivers. So what we had basically when we had that first one, if you have a reverse engineered VM protect, you don't want to do that usually. It takes a lot of time, and in a field that is so dynamic as ours, you usually don't have the time in an incident, well, okay, I will need like 2 weeks or 2 months to reverse engineer VM protect now. So you have to hurry up a little bit. We knew, okay, majority of them are packed with VM protect or some other commercial packers like Themida. It is always a driver in our case. And that signer name is Microsoft Hardware Publisher Program. So it turns out that there are not many drivers signed with VM protect, packed with VM protect, carrying that signature, and that are drivers that are not that are legitimate. So that made it a little bit easier to search for variants. So what we found is, like Andrew already said, a large number of them were signed with that WHQL, or that Microsoft Windows Publisher certificate. They were packed with VM protect. Many of them used very distinct symbolic names that did not look that legitimate, like that KAPC helper link, label XX device, projector device, and some variants of that, sometimes some randomized name. Many of them were variants of that poor try burned cigar variant. Not all of them were signed by that hardware compatibility publisher certificate. Some of them also had NVIDIA, these weird Chinese signature names that do not look like they are legitimate companies. So really a great variety in there. Many of them, also some of them were not that same variant as that poor try or burned cigar. So we digged a little bit deeper and checked what kind of behavior the other files showed, and it turned out quite interesting. So we found 2 EDR killers. One is that burned cigar poor try variant that is usually shipped with ZoneStop, which is basically the loader it always interacts with to kill EDR agents. The second one, EDR killer, was called ACCPT rootkit. So if you looked into that one, it only targeted Chinese anti-malware drivers. So from looking at some rootkits, very often, if they are like targeting the Chinese area, they are often some cheat like anti-gaming drivers or rootkits that target like really gamers that try to get some cheat somewhere. Then some older rootkits like FK Undead was discovered, I think, 2019 or 20, which is a very modular one that can control SSL traffic, modify content if you visit some websites through injection. Then NetFilter rootkit, which is basically like the name kind of suggests it's a network sniffer. It mainly monitors traffic and redirects the traffic to a number of domains. And 5sys, which is very similar to that FK Undead rootkit, which is very modular. So depending when it runs, it will actually load different modules depending on the use case it's currently, or the action it currently targets to execute. So yeah, we found a couple of different variants. That's it for the technical part. I think Andrew had not to say something at the end here.
Oh yeah, no, I just wanted to, well, I think I've already said, like, it was a really good partnership between us. I wanted to mention that some of the other malware that we saw that was using this technique, that it was using, some of it communicated over command and control with these algorithmically generated domain names, or DGAs. And that all of those command and control domains all use the .xyz top-level domain. So again, a real legit like TLD for everyone to use. But then that we were seeing some of these that had been built as early as April 2021. And that indicated to me that there had been a significant problem for a while, that these drivers had been, someone had penetrated this mechanism, and that they had been getting stuff signed with Microsoft's code for almost 2 years at the point where we, finally were getting close to finishing it. So yeah, that was it. And I just wanted to say thank you all for the collaboration and the cooperation. And we look forward to helping you all protect everyone else next time. Thank you.